Hello everyone. Now taking this graph into consideration, how can we determine if the function is continuous at point 0, 1, 2, 3, 4, and finally 5. Now, for the function to be continuous at a point, we can summarize all the conditions under one equation, right? And that is that I think it's better if I write it this way. So the limit of f of x, right, of our function as x approaches a particular value, let's take a, should be equal to the value of the function at that point. Now, for this condition to be possible, that is, for the limit of f of x as x approaches a particular value to exist, the left hand limit and the right hand limit should exist, right? So the limit of f of x as x approaches a from the left should exist, and it should be equal to the limit of f of x as x approaches a from the right. And finally, the last condition, f of a, right, should be defined. Now we'll be explaining what everything means over here in the example. Now, is the function continuous at 0? Now, for the function to be continuous at 0, the limit of f of x as x approaches 0, right, 0 must exist. And for that to exist, the left hand limit and the right hand limit must exist. Now, as we approach the function from the left, right, we notice that the function approaches 1, right, 1. That's the point at which the function crosses that's the point at which the function crosses the y-axis, right, mapping from 0. You get it? Also, from the right hand limit is 0. Now, the second condition is that f of 0 must be defined, right? And mapping to 0, mapping from 0, we can clearly see that f of 0 is defined. I know it might not be clear right now, but let's look at the other examples and this will be clearer once we are done. Now, is the function continuous at x equal to 1? Now, considering the left and right hand limits, the left hand limit as we approach 1 and the right hand limit as we approach 1, we notice that as we approach 1, the function approaches 1, right? So the limit of f of x as x approaches 1 is 1, right? We can simply map our function to the y-axis, getting 1. Now, take note of this whole, right? It's not there for fun. Now, f of 1, what's the value of f of 1? Is f of 1 defined? The answer is no. Now, why isn't f of 1 defined? Now, mapping f of 1 from the x-axis, right, we see that there is no value for f of 1 at 1, right? So at 1 there is no value because there's a hole in our graph, right? So f of 1 is not defined. Now, the reason why the limit as x approaches 1 is defined is that for limits we are not really considering the value at 1, we are considering the value as we approach the value 1, right? That's why as we approach 1 from the left and right hand side, we still get 1 for our answer, but at the point 1, the function is not defined. Now let's consider at 2 also, right? Now at 2 is the function defined, so we can see that as we approach from the left and from the right, we approach 2, right? 2. So as we approach 2, we also, as we approach 2 from the left and right hand side, right, we obtain the limit as 2, right? So 2 2. Now, is the function defined? Yes, it's defined, because at 2 the function has been defined as 1. So f of 2 has been defined as 1, right, by this point over here. So f of 2 is defined as 1, as 1. What's the limit of f of x as x approaches 2? Is 2, right? And since these two are not equal, right, the limit is not continuous. So again, at f equal to 2, the limit is not continuous. Now let's consider at x equal to 3. So now, approaching from the left, right, and from the right, we notice that we obtain 0. The value of the limits as we approach from the left and the right hand side is actually taken on the y-axis, right? So as we approach 3 from the left and right hand side, we notice that we obtain a y value as 0. Now, what is f of 3? Mapping, tracing the value of f of 3 on the graph, we notice that f of 3 is right at its origin, right? Therefore, we can say that f of 3 is also equal to 0. Therefore, the function is continuous at f equal to 3. Now, let's consider f, the function, when x is equal to 4. Now, considering our left hand limit and considering our right hand limit as we approach from the left and right respectively, we notice that as we approach from the left, right, as we approach 4 from the left, we are approaching 4 from the left, and tracing it to the y-axis, we obtain the limit as we approach 4 from the left as 2, right, as 2. Now, what is the value when we approach 4 from the right? As you approach 4 from the right, right, immediately we get to 4, we start to trace to the y-axis. We obtain the value as 1. This means that the left and right limits are not equal. Therefore, the function is not continuous. Because the left and right limits are not equal, the limit as x approaches 4 does not exist for it to even be equal to f of 4, right? Therefore, there is a discontinuity at f equal to 4. Please stay with me. After we'll identify the types of discontinuities that we are getting for the various values of x. Now, let's consider at x equal to 5. So now, from 5, from the left as we approach 5, right, from the left as we approach 5, and also from the right as we approach 5, we notice that the curve goes upwards, right? So the limit as we approach 5 from the left and right goes on and on and on and on and on. Therefore, the limit does not exist since the limit approaches infinity at the value x equal to 5. Therefore, the limit does not exist. Now, at 1 and 2, at 1 and 2, right? At 1 and 2. So this is 1 and this is 2. As you said earlier, the limit exists, right? The limit exists because the left and right hand limits, the one-sided limits exist. Therefore, the limit exists. But as we said, it is discontinuous because f of a, right, is not defined, or f of a is not equal to the limit, right? Now, the type of discontinuities here and here also is known as removable discontinuities. Now, why do we call this removable discontinuities? Now, this is called removable discontinuities because we can redefine our function for the value for the function to be continuous at 1, right? Now we can say that at x equal to 1, right, f of 1 is equal to 1. Now remember, we don't have a value for f of 1 over here, right? At f of 1, we have a whole here. Therefore, defining the value of f of 1 as 1, right? 1, because when we trace from x, when we trace to the curve and map to the y-axis, we obtain 1, right? So now when we do this, the limit as x approaches 1 from the left and right hand side being equal to 1 also equals the function as 1. Therefore, we can redefine our limit, making it continuous. Now, at x equal to 2, the limit has been defined as f of 2 being equal to 1, right? So, to make this continuous at f of 2, you can simply say that for the limits to for the function to be continuous at 2, f of 2 should be equal to 2, right? And because we can redefine our functions, we say that these two types of discontinuities are known as removable discontinuities. Now, let's consider the discontinuity at 4. Now, we can clearly see that the left and right hand limits are not equal, right? The left hand side, the limits from the left is not equal to the limits from the right. And in this situation, we have what we call a jump discontinuity, right? So we can see a jump from this point to this point, right? A jump discontinuity, right? So we can't redefine this to make the function continuous. Now at 5, we have an infinite discontinuity. Of course, the left hand limit approaches infinity and the right hand limit also approaches infinity. This is Teach Me Maths. If you've watched to this point, I know you'll be liking to watch more videos like this. Please subscribe to be kept updated. Thank you and